in this talk we start the analysis of one dimensional wave equation. So, probably in the next 5 or 6 lectures we will be studying many aspects of this one dimensional equations. So, let me write down the equation first. So, this is a second order linear equation given by u t t minus c square u x x equal to 0. So, this is called homogeneous wave equation, and c is a positive constant known as speed of propagation. So, we will see little later why it represents speed of propagation. So, this t is the time variable. So, let me just introduce this time variable, and x is the space variable. So, x space variable. So, it is called one dimensional wave equation because x is a real variable. So, if you replace this u x x by the Laplacian u, so this just so, and Laplacian is the Laplacian in n variables. So, this you will study during the discussion on Laplace and Poisson equation, Laplacian in n variables. And then this is termed as n dimensional wave equation. Okay. A physical situation where this equation arises, I just briefly discussed that. So, physical situation. So, that generally represents vibrations in a string, physical situation. So, this so this is the x axis and this is the u axis, and so as typical string. So, you are plucking it. So, this is string. I am not going to give the details, but just say how it is derived. So, you take two close by points on the x axis, x plus delta x, okay, and you calculate the force acting at these 2 points. So, that is the, so they act on the along the tangent to the string, call it T, and then you apply Newton's second law, apply Newton's second law, which is mass times acceleration, and that gives you del square u by del t squared term, and force gives you del square u by del x, del square u by del x square term, and that is how you derive the wave equation. It is important that, so that while applying this Newton's second law, some approximations are made, so that you can see it in our book on PDE. Some approximations regarding small oscillations. So, this is not valid for large oscillations. So, if you take arbitrary oscillations, then the equation becomes nonlinear, which is more difficult to analyze. Okay. So, again go back to okay. So, return to the wave equation again. So, we have already learned in the lectures on classification of second order equations. So, this has two real and distinct characteristics. And so, it belongs to, and so belongs to hyperbolic class. So, this is a typical example of a hyperbolic equation. So, what are the characteristics? So, so you see the characteristic equation, maybe I will use different notation here. So, that is, so characteristic roots are plus or minus c. Okay. Hence, the characteristics, so characteristics are obtained by solving the first order equations. Characteristics are given by dx by dt is equal to plus or minus c. Okay. And these are the straight lines. So, in this case straight lines, x plus or minus c t equal to constant. So, let me just draw some pictures. So, typically you so this is x axis and this is t axis. Okay. So, the characteristics, so we have them. So, two families of straight lines. So, these are x minus c t, maybe let me just, so this is x minus c t equal to constants. So, this is one family of characteristics and another family. So, let me use different color. So, just okay, so this is x plus c t equal to constant. So, the blue ones have slope, this is slope. So, you are drawing, remember this, we are drawing x axis horizontal and t is vertical. So, slope is 1 by c and the red one's slope is minus 1 by c. Okay. So, this suggests us to use characteristic variables. So, we are changing the coordinates x t to xi tau. So, let me write that. So, what is xi? Xi is x plus c t and tau is x minus c t. Okay. And this change of variables suggested by the characteristics explained in the previous sheet. Okay. The important thing to note is this we already learnt in the during the classification of second order equations. The important thing is this is non singular change of variables, that is very important. So, if you compute the Jacobian, you see that it is non-zero everywhere, change of variable. So, this helps us going from one set of variables to another set of coordinate system. Okay. So, it is easy to see that. So, this implies, so the inverse if you call, so from xi tau we can go to x t. So, the x is just you do that simple algebra xi plus tau and t is 1 by 2 c xi minus tau. So, now we will see that simple implicit differentiation gives us. So, next compute u xi. Okay. So, this is by implicit differentiation. So, this is u x x xi, let me write it. So, you can work out t xi. Okay. And x xi you see is half and t xi is also 1 by 2 c. So, you get 1 by 2 c. So, simplification c u x plus u t. And now, you do differentiation with respect to tau. So, u xi tau. So, this is 1 by 2 c is constant, there is a c constant there, and now I have to do this differentiation of u x with respect to tau. So, for that thing again I use implicit differentiation. So, x tau plus u x t t tau. So, that is with respect to u x, and similarly I do with u t and t tau. Okay. So, if you now simplify, and now x tau is again half, but t tau is minus 1 by 2 c. So, you see that you finally get there is 1 by 2 c here, okay, 1 by 2 c. So, 1 by 4 c c square. So, some terms get cancelled and you can easily verify that. So, maybe c square here, 2 c you get, and that is equal to 0. Okay. So, with this change of variable, we see that the wave equation reduces to, thus in xi tau variables we obtain u xi tau equal to 0. So, the wave equation reduces to the simpler form. So, it is still second order, but this one we can integrate easily. So, integrate easily. Wave equation we could not do, but now in this characteristic variables we can easily integrate. For example, first you integrate with respect to tau. So, you get u xi. So, this is purely a function of xi. So, when I differentiate this with respect to tau, it will be 0. And one more integration. So, if I integrate this is a function of only xi. So, this so when I integrate again with respect to xi, so I will get another function of xi, but that constant of integration can be a function of tau. So, that leads to one more integration. So, u is equal to, again I write it f xi, but this is another different function because this integration of that, but this one I have g tau. Okay. So, you can easily verify that if f and g are 2 times differentiable. So, any function of this form satisfies u xi tau equal to 0. Okay. So, therefore, the general solution of, now we go back to the x t variables, original variables, general solution of the wave equation is given by u x t is equal to f of x plus c t, xi is x plus c t and tau is x minus c t. Okay. So, where f and g are arbitrary C2 functions. So, C2 means 2 times continuously differentiable functions. So, where f g are C2 functions. So, you can also easily verify if u is given by that, and if f g are two C2 functions, then directly you can differentiate and verify that u indeed satisfies the wave equation. So, there is no difficulty in doing that thing. Okay. So, in order to determine this f and g, so there are two these are two unknown functions f and g. So, we need to impose two conditions in order to compute f and g, okay. And that is done by imposing two initial conditions. So, this is called initial value problem, and that okay, impose two initial conditions. Okay. In order to find f and g, and this will lead to D'Alembert's formula, which we will take up in the next class.